So then we will, this session is a plenary lecture of this conference. The speaker is Professor Robert Jerrard from University of Toronto. He will talk about vortex filament reconnection in 3D critical Abelian Higgs model. Professor.
Okay, hear me? Okay, well, I'd like to start by thanking the organizers for the invitation to speak at this very impressive conference. And so all of the new work I'll talk about today is joint work with my PhD student, Amirmasoud, who is actually starting a postdoc appointment here at BIMSA within a few months, as soon as he can take care of his paperwork. And so he will be here. And good. And so I'm talking about vortex filament reconnection. This, the background is there are a lot of, say, physical phenomena in which one can see coherent vortex filaments. And so in these, these are visible both in physical phenomena and experiments, and also in PDEs that model, in solutions of PDEs that model this phenomena. And so one might ask, once we understand the dynamics of vortex filaments in isolation, what happens if two filaments collide? And so, I'll first review this question of the dynamics of vortex filaments and the issue of reconnection. I'll discuss this in the context of the Abelian Higgs model, so I'll spend some time introducing that equation. Then I will state the main result about the Abelian Higgs model and discuss some implications for the question of reconnection. And finally, I'll discuss the proof briefly. So so as I said, many equations are known to have solutions with, say, coherent concentrated vortex filaments. I'll show you an image in a second. These often have some stability, so they're stable enough that you can see them in numerical experiments and in physical phenomena. And the reconnection question is, if two filaments are evolving and at some point they collide, what happens next? And so we can imagine or we can imagine a number of possible outcomes, but two possibilities one might think of are, they might, say, pass through each other without interacting, as in the above picture, or they may change topology. And so here I can see in this picture, the bottom half of the blue filament has joined to the top half of the green filament, and vice versa. And so there's been some exchange of topology. This latter scenario is what is meant by reconnection. And so the question is generally which of these happens, or does something altogether different happen as the outcome of a collision of vortex filaments? And so, in fact, this reconnection is expected to be generic under many circumstances. So it's seen in numerical simulations and experiments, and it can be seen in daily life. And so these are images from a movie that was a video recorded by my collaborator, D.A. Smets, at an air show outside of Paris. Here, this airplane is flying, and as it flies, it sheds vortices off the wings. And so these are counter-rotating vortices. But then after the airplane has left the picture, these vortex filaments, and so you can see they have some stability. They don't disappear immediately. They persist, and they evolve. And in this picture, eventually, at this moment, they collide here. If I'd show the picture a bit later, they round off like this. So one filament connects there, and the other does this. So this is really a reconnection. The topology changes as the outcome. And in fact, I would say, okay, there's some exotic gauge theories in which two filaments cannot penetrate each other. And so those are, but leaving those aside, I do not know of any example anywhere, numerical or empirical or experimental, of a collision leading to a non-reconnection. I don't know of any example of this happening in any collision. So, okay, here's what I know. You can go on YouTube and search for vortex collisions, and you'll see a lot of videos of experiments with water and with superfluids. And you can see these vortices in these physical systems, and you'll see collisions, and you will always, always, always see reconnection, and you will never see the filaments passing through each other. And so this seems to be a very robust phenomenon okay, I hesitate to call it universal, but say universal across a wide range of models and parameters. But there's no very good mathematical explanation for it to date. Okay, and so the situations in which one might expect to observe reconnection are situations in which one observes stable vortex filament dynamics. And so as soon as I have vortices moving around, these one-dimensional curves move around in R3, I can expect to see situations in which two of them collide. And so let me first review what's known about vortex filament dynamics in three space dimensions. And so I would say this is well understood in, okay, I'd call this the ungauged Ginzburg-Landau heat flow. So these first two are heat equations. The second example is the first example coupled to an electromagnetic potential. And in both cases, it's known that vortex filaments persist and evolve. In every case, the theorems I'm discussing here and the say conjectures on the next page suggest that in solutions of these equations, vortex filaments persist and they evolve in the limit s, say in the limit when this parameter epsilon tends to 0. They evolve by some geometric evolution equation. And so for the parabolic equations here, the limiting geometric evolution equation is the codimension 2 mean curvature flow, or the codimension 2 curvature flow. This was proved first by myself and Soner Lin in about 25 years ago, for where we started with a smooth solution of the limiting geometric problem and constructed and showed that for initial data who's suitably close to that smooth solution, that the vortex filaments evolve by mean curvature flow. Then there was a series of more general papers culminating in this work of Bethwell, Orlandi, Smets. These results are actually valid in Rn for arbitrary n greater than 3, and with always the same law of motion, the codimension 2 mean curvature flow. The theorem of Bethwell, Orlandi, Smets says, roughly speaking, that vortex submanifolds, they identify a limiting submanifold around which the vorticity and energy concentrate. And they show that this submanifold exists globally in time. And globally in time, it's a weak solution of this codimension 2 mean curvature flow in a measured theoretic sense. Essentially, the same result was proved by Parisi, Pagati, Stern by the Abelian Higgs heat flow just about within the last, this was finished about a year ago and it's just been accepted, I believe. It just appeared in GAFA. There are parallel results for the wave equation, both the ungauged wave equation and the wave equation coupled to an electromagnetic potential. These are both from a paper of mine about 10 or more years ago. And these results are weaker. So these here we require a smooth solution of the limiting geometric evolution equation, which is the codimension 2. It's what's called the time-like minimal surface equation in Minkowski space for codimension 2 surfaces. This is a wave equation for curves evolving in R3, a quasi-linear wave equation. Okay, and so I would like to just make a few results. And so all of these, the tools in these are, say, geometric analysis. They have a geometric measure theory flavor, and they use tools from the calculus variations. And so, for example, especially for the ones connecting this equation to mean curvature flow, there's a huge geometric analysis literature on mean curvature flow involving things like the monotonicity formulas and so on to control the flow. And so the idea, or the starting point of these analyses is to try to transpose ideas used in the mean curvature flow setting to this PD analysis. And okay, in all these results, vortex filaments are identified as concentration sets of vorticity and energy. And so for example, we can take the limit as epsilon goes to 0, and the theorem would state that in the limit, the vorticity concentrates around a codimension 2 submanifold, which evolves by the right geometric evolution equation. And then again, the other point I want to make is that the laws of motion here, the codimension 2 mean curvature flow, and this time-like minimal surface equation they will give rise to collisions of vortex filaments. Okay, so then next, so there are some equations. So these are equations. These are actually the ones you can see on YouTube if you look for videos. These are fluids. Navier-Stokes, and the Gross-Petitev's equation models some superfluids, and so the conjecture is that in both cases there are say in the limit as epsilon tends to 0, the will concentrate around a codimension 2 submanifold that evolves by what's called the binormal curvature flow, and so in the parabolic and hyperbolic cases, the limiting law of motion can be seen as, say, a heat flow for curves and a natural wave equation for curves. This you should think of as being the natural Schrodinger equation for curves in R3. This is not proved. This is, I consider this to be the most significant open problem in this area, is to justify binormal curvature flow as the limiting law of motion here. I should say, in this case, this can be viewed as a open problem dating to 1906, when the first paper predicting this was published by someone named Darius, who was a student of Geevechi. And I should mention there's some results of Jingxuan Zhang on this problem, which don't quite address the same regime. So they deal with an extremely small perturbation of a straight vortex filament. A perturbation here, epsilon is roughly the vortex core size. And if I understood correctly Jingxuan's result, the perturbation, he's considering a straight line perturbed by things of order power larger than, epsilon to power larger than 1. And so these are perturbations who sort of stay within the vortex core, if I understand correctly. So here are some of the results. So essentially results are known for rotational symmetry, in which case the dynamics is just a rigid motion of circles, or there are more recent results by Davila, Del Pino, and Musso on what's called leapfrogging of vortex filaments. These are very deep penetrating results. There are similar results in Marchioro and co-authors preprinted within the last 6 months, I believe. And similarly, there are results on rigid motion of Euler and Gross-Petitevsky vortex filaments with helical symmetry. And so, if you start with the helix, this will correspond to a translating solution of the conjectured limiting law of motion. These authors have constructed solutions of these equations which exhibit this kind of behavior. This is Dalman and Tao and co-authors. They have several results within the last year or two. There are conditional proofs of the conditional derivation of the law of motion for these two binormal curvature flow by myself and Slice for Euler and myself alone for Gross-Petitevsky. And then there's work on Navier-Stokes with rotational symmetry of Gallet and Schwerak. Gluing methods, if you like, say constructive arguments are used in the work of Davila, Del Pino, Musso, and Wei. And also for elliptic problems involving Abelian Higgs vortex filaments and work of Badra and Del Pino. But by and large, they have not yet been used very much for this class of problems. For, say, vortex filament dynamics in these problems in the 3D setting without symmetry. Okay, oops. So what's known about reconnection? Yes? Sure.
Vortex is like a solitonic solution of
okay, so you can think of, so these things are like solitonic solutions. And so an example would be the first result of Marchioro from some results of Marchioro from the 90s would construct a solution with the vorticity concentrating so take a circle of radius r, fix a parameter epsilon greater than 0. The vorticity will concentrate in the tube of radius epsilon around the circle, and the whole thing will translate with constant velocity. So that is a kind of a solitonic character. And these helical solutions have have a similar character. Okay. And so, okay, what's the reconnection? It definitely does not occur in regular systems with Euler, so this is a consequence of the first thing you learn in the fluid dynamics class, the transport of Euler vortex filaments by the flow. Solutions exhibiting reconnection. So there are two very interesting papers of Enciso and Pratasalis, one of them joint with Luca, in which they construct something like vortex reconnection. This is a different regime from the one I'm interested in. So, for example, in the Geevechi result, their regime has great flexibility in dynamics. So one difference is when they say vortex filament, they mean a single integral curve of the vorticity vector field. Whereas in the works discussed here, I'm looking for L1 macroscopic L1 concentrations of vorticity. And so in other words, if you look at a video on YouTube, you can see L1 concentration of vorticity. You can't see a single integral curve of the vorticity vector field. It's and so in this regime, also, for example, the Geevechi is studied in a nearly linear regime, so as a perturbation of the linear Schrödinger equation. So if you like, this is when this epsilon tends to infinity rather than to zero. And they show that in this regime, for example, they can, so there's enormous flexibility in vortex dynamics. They can take a codimension 2 submanifold and evolve it in a more or less arbitrary way with reconnection, or else they can have collisions with no reconnection. They can do what they want, and then they can construct a solution of Geevechi that stays close to that. By first doing this for the with exactly one integral curve of the vorticity vector field, who stays close to the submanifold they started with. They do this by first studying the linear Schrödinger equation and then viewing the nonlinear Schrödinger equation as a perturbation. Okay, I mentioned these results, the global and time results on vortex dynamics in the two heat equations mentioned above, the Ginzburg-Landau heat flow with and without coupling to a magnetic potential. And so these results are valid globally in time. And so in particular, they cover situations in which there are collisions, but they don't resolve what happens after those collisions. They don't say if we have the situation of things, they don't resolve the question here. And so either of these are acceptable weak solutions. They don't tell you which one occurs. And then, there's a large physics literature. And so in Vortex and Geevechi, this reconnection is seen as a big mechanism in either quantum turbulence or fluid turbulence. And also there's a big literature on cosmic strings, what are called cosmic strings. In this case, the physicists basically take it for granted that reconnection will always happen when filaments collide, and they take this as a starting point for further speculations on the effects of cosmic strings on the distribution of matter in the universe, et cetera. So these, there's this large physics literature, but it's I would say, from a mathematical point of view, it's pretty heuristic, if even heuristic. Okay. And so, another result that we mentioned. So an approach to filament collision in the Euler equation is described in formal work of these authors, Damodar and Klein and Maida in 1995. And so they drive a system of PDEs describing nearly parallel vortex filaments. The system combines the self-induced motion of the filaments after linearization, because the filaments are nearly straight, and also pairwise interactions. Then in this reduced model, collisions filaments are studied in this work of Bonica, Fau, and Mio. The Klein, Damodar, and Maida system was rigorously justified by me and Smets a few years ago. And so this is also, I would say, the closest result to understanding the, so here we essentially derive we prove a linearized version of the conjecture law of motion for this vortex filaments in this setting. And, but still this connection, this approach, I would say, cannot hope to resolve the reconnection question. The tools just will not work. Okay, and so what I'll study instead, the remainder of the talk will focus on the Abelian Higgs model. And everything I discuss will also be valid for a parabolic counterpart. So this is the Abelian Higgs model is a hyperbolic equation. So d sub 0 is a time derivative, d sub k are spatial derivatives. Here I'm in 3 space dimensions and 1 time dimension, and I'm summing implicitly over k. And so this, the capital D is a covariant derivative, if you like. And so the unknowns here are this phi, who is a complex valued map, and A, who is a map taking values in R4, which I'll identify sometimes as the coefficients of a one form here. So the A appears when we differentiate. I differentiate in a way that involves this one form A. And so this is a covariant derivative. And so then here we see the covariant second time derivative, the covariant Laplacian. And then there's a parameter lambda here, which I'll set equal to 1 in a second. This F0 alpha is, so here, physically A is a connection one form who generates the electromagnetic fields. And so F alpha beta will be components of the electric field or the magnetic field. If either alpha or beta is 0, then those will be a component of the electric field. If alpha and beta are both between 1 and 3, this is the component of the magnetic field. And so this is if I only look at, if I forget about phi and only look at this equation, then this is exactly Maxwell's equations in a vacuum. And so the equation describes a coupling of Maxwell's equations to a current generated by the so-called Higgs field. Okay, and so as I think I say on the next slide, so the main point is it's a nonlinear equation, coupling electromagnetism to this other field. And okay, so let's say this here. I'll always consider the case lambda equals 1 for reasons I'll discuss in a moment. So this is, the title of the talk refers to the critical Abelian Higgs model. Lambda equals 1 is the critical case. And let me remark first that the Abelian Higgs model arises in high energy physics and cosmology. And so the studies I refer to of cosmic strings from the 80s and 90s in the physics literature, the starting point of those studies is a consideration of the Abelian Higgs model and dynamics of vortex filaments in that model. Okay, this is a parabolic version of the above equation who arises in the context of superconductivity. Both these equations, the hyperbolic and parabolic, have a huge symmetry group. And so if phi comma A is any solution pair, and if chi is arbitrary, smooth enough function, then I can act on the pair phi A in this way to generate a new solution. E to the I chi phi and A plus d chi is also a solution. And so this is an infinite dimensional symmetry group acting on the solutions of the equation. Note that we can never have well-posedness in either of these equations without fixing this degree of freedom, because there can't be uniqueness. These equations are terribly, terribly underdetermined because I can transform them in an arbitrary way. So I can take initial data, I can take one solution, I have enormous freedom to change it at later times in a way that is the initial data. And so the way that this degree of freedom is fixed, the choice of gauge, is a key analytic issue in every problem involving these equations. Okay, now let me quickly review some aspects of the critical case lambda equals 1. So here, as I'll remind you, a complete classification of solutions is known in 2D. And so this is work that was developed over the main results, the initial results were due to Bogomolny. I mean, there's an important book of Jaffe and Taubes in 1980 that built on contributions from Bogomolny and Witten a few years before that. And so the work above here is Jaffe and Taubes and predecessors, and the work below here is I'll get to in a second. And so here's what this says. There's a complete classification of solutions. And so first of all, every finite energy pair has a well-defined integer vortex number, capital N. And the way one should think of this is here I have this wave function phi. It turns out that for finite energy, so due to the presence of this term in the equation, there's an associated energy. And for finite energy solutions, the energy contains this quantity, phi squared minus 1 squared. And so for finite energy solutions, the modulus of phi will tend to 1 at infinity. So one can imagine that at infinity we have a map taking values in the unit circle S1, and it has a certain winding number. The phase winds around the origin n times. That is the vortex number. And so every finite energy pair has a well-defined vortex number n. So the space of finite energy pairs phi comma a is a disjoint union of, say, n of pairs with vortex number n. And I will let m sub n denote the space of gauge equivalence classes of n vortex solutions. So these are solutions of, so here I'm considering the equation in 2D, the Abelian Higgs model, where I forget the time variable and I have only 2 spatial dimensions and lambda is equal to 1. And so this is an elliptic problem. And so an n vortex solution will be a solution who lives in this space of the solution with vortex number n of those equations. And then I'm interested in solutions modulo this equivalence relation, where, let's see, is there any chalk here? I don't. Here it is. I'm always interested in solutions modulo this equivalence relation. And so here's what this space looks like. It's a 2n-dimensional space, a real 2n-dimensional space. And so the theorem of, say, Geevechi and Taubes is that there are bijections as follows. So for a point Q in R2n, I can identify that with a point in Cn. Clearly, I can then uniquely associate to that a polynomial whose coefficients are the n complex numbers, Q1 up to Qn, okay? And then I can uniquely associate to that the n roots of the polynomial, counting multiplicity. And the theorem says that given this data, there's exactly one, here I mean an equivalence class of solutions in this moduli space. Note that the modulus of u, the modulus of phi is independent of, depends only on the equivalence class. Okay. There's a unique equivalence class of solutions for which, so what this says is that it says, as I've written here, that the modulus of phi vanishes at exactly the same points and to the same order as the polynomial here. So it has the same, so if I know the roots and I know the vanishing order, then that exactly determines one unique equivalence class of solutions. Okay, this is the theorem of Geevechi and Taubes and so on. And there's it's not a totally explicit description. There's a reduction of the system equations to a scalar equation, a nonlinear scalar equation out of which everything is then constructed. Okay, moreover, and so here, this I believe was first proposed by Manton in a physics perspective and proved first by Stewart for n equals 2, and then by Palveda more generally for larger n. So there's a natural Riemannian metric on this moduli space. And let me tell you how it's constructed if I have a few moments. Right. Very quickly, I have this M, and it's a finite dimensional manifold. And then I can associate with it pairs phi and A over here. But you see, for each point, if I take a given, particular pair of phi A, particular n vortex solutions, well, then there's this infinite dimensional symmetry group the orbit under the gauge symmetry of that solution. And so there's this much bigger space. Okay, now I suppose I have a point here and a tangent vector, and I'd like to ask what's the natural norm for this tangent vector? Well, I can map it over to here, and then I can map the path over to here. But I have a huge amount of degrees of freedom in how I lift this path to here because of this massive symmetry. And so the idea is just to choose the lift this path in such a way that and then compute the L2 norm, just the L2 norm of the tangent vector in this setting, and do this in a way that minimizes, choose the lifting who gives the minimal L2 norm. So it inherits a Riemannian metric in a very natural way from this space with this symmetry root. And then the other part of the theorem is that these Q's provide a good coordinate system for the moduli space. So if I define this metric tensor, it's smooth and it's non-degenerate. It never vanishes. Good. So this is the moduli space. Let me make some examples. Let me make some remarks. And so these roots, Z1 up to Zn of the polynomial, are called the vortex centers. Actually, this should be a Q. And we can say the center of vorticity is just the mean points. And okay, there is indeed a physical quantity called vorticity. I won't define it. That concentration near the vortex centers. So I'll refer to this later on. So assume that I have only two vortices. I'm in the two vortice moduli space, and the center of vorticity is 0. Then I have two vortices at locations Z1 and Z2, but Z2 is minus Z1 because the center of vorticity is 0. And so on the one hand, the polynomial with those roots is Z squared minus Z1 squared. On the other hand, the polynomial P of ZQ by definition is this. I've changed the sign for convenience. And so I can see in this situation, when the center of vorticity is 0, this Q1 always vanishes, and Q2 is related to the vortex locations in this way. So Q1 vanishes, and Q2 is equal to Z1 squared of Z1 is one of the vortex locations. Okay, and so in this situation, we can say there's a reduced moduli space, which is just isomorphic to C, and in this case, the map that takes me from the reduced moduli space to the vortex configurations in the plane is just the square root map. So if I have M2 reduced, it looks like C, and okay, and so for example, a smooth trajectory here will not look like a smooth trajectory over there. Let me show how this goes. I have a video that I think will work. This may take a second to load. Okay, we're connecting. But what I will show here is just a curve moving with constant velocity along the real axis here. And what you will see on the other side, it starts at, say, -1. Then the two vortices will be at plus minus I. Okay, here it is. And so this is a perfectly smooth path in the moduli space. It doesn't look smooth here. You'll see a square root type behavior in the velocity. You also see, so I mean smooth in a kind of a naive sense. It doesn't look very smooth. Having worked to produce this, these animations were half written by a chatbot. I did half by myself. So there it is. And okay, and so then moving on. And so Manton argued that low energy solutions of the Abelian Higgs model in two space dimensions should have the following structure. They should look like, so essentially this alpha is the, so here the one form has two components in the x directions and one component in the t direction. These are the x components and this is the t component. And so this would just be a point phi alpha in the moduli space. So I may choose a distinguished representative over here in the moduli space. And so the suggestion was that if Q that at every time the configuration should look like one of these. It should be close to a static solution with parameters, and the parameters evolve by geodesic flow in the moduli space. Okay. He also made a solution for the non-Abelian Yang-Mills Higgs model. Motivated in part by this, in the 1980s, a great deal of rigorous work was done on the geometry of moduli space, especially for this non-Abelian model. There's some non-rigorous physics literature. Then Stewart in 1994 proved rigorously that this prediction is true for n equals 2 vortices. He also did the Yang-Mills Higgs model. And then Pavlov extended Stewart's result to arbitrary n. And so here I was going to visualize Stewart's result. This is actually exactly the same video as last time, the one I already showed. Let's look at the next one. So you can also imagine a trajectory who does not quite pass through the origin. Okay, I don't want to waste too much time on this. Let's not bother. Okay, and so the main result that I want to talk about is extension of these results to higher dimensions. And so we're considering wave maps from 3 space dimensions. The Abelian Higgs model in 3 dimensions, and the theorem. I have here a kind of a formal argument, but I think I'll skip it in the interest of time. Yes, I will. And so here's what the theorem is. So we now I'm considering the Abelian Higgs model in 3 dimensions, and so the phi is again a complex valued function. Say a sub a would be so here t is time, x is a function, x are is the variable, say the 2-dimensional variable for this thing, and then y is a third variable. And so I'd like to think of y as being a horizontal variable, and then y as being a vertical variable, and x as being the variables in the horizontal plane, and then t is time. And so what this says is it can reconstruct solutions such that if I fix time, then, and I look at any height y, if I look at a horizontal cross section, I will see something who's very close to one of these static 2D solutions. And then there are these parameters who evolve slowly in the vertical y variable and in the time variable. And the theorem is that if these evolve by what's called the wave map equation into the moduli space, then we can construct such a solution with small error terms. Okay, and so these are estimates of the error terms. And then let me mark the theorem actually remains valid. There's a version for the Abelian Higgs heat flow, or indeed we have a 1-parameter family of, say, damped Abelian Higgs equations that interpolate between the heat flow and the wave equation, the Abelian Higgs model. It's also true in arbitrary higher dimensions with a suitable generalization. Okay, and so this is the theorem I would like to discuss in the remaining time. And so before I talk, what I want to do is talk about some consequences for reconnection, and then I'll briefly discuss the proof. And so let me again consider n equals 2, and let me again work in the setting of the reduced moduli space. And so here I have, so what happens is, at a fixed time t, in every horizontal slice, I see a small perturbation of this static solution who's characterized by its vortex locations. And so as I move up and down the y-axis, the positions of the vortices will move, and so they'll sweep out, say, in this case, n equals 2 curves, and then the curves evolve in time. And but I want to assume that at every height and at every time, just for simplicity, that the center of vorticity is at the origin. If you put this, you can construct initial data, so this certainly happens. So this is restricted, but it's not unrealistic. And so then we'll have, say, a wave map taking values into this reduced moduli space. And so this looks like the complex plane, but it has a metric, a funny metric that inherits in the way I've described. I claim that a sufficient condition for reconnection in this setting is if Q at a certain time, at a certain point, y naught, t naught passes through the origin, and if the time and y derivatives of Q are linearly independent. And so let's look at these animations if we can. And okay, it's taking some time to buffer. And so here I'll have what I will have is I'll start at time 0 with a curve that starts, say, here at y equals minus infinity and ends up here at y equals plus infinity. And as y increases, it will connect them, say, through the lower half plane. And then I want to imagine that as t increases, the curve moves up. Okay, here it is. Good. And so what we see here, let's run it again. Okay, so the point is, if the curve is in the lower half plane, then the corresponding trajectory of the vortices will start with two vortices here. These are two vortices on the imaginary axis. This is y equals minus infinity down here. It'll end up at y equals plus infinity with two vortices on the real axis, right? The two squares of this number. And then if I have this curve who stays in the lower half plane, the square roots will be, I guess, in the, well, as you can see, in the second and fourth quadrants, right? So if the curve's in the lower half plane and I take the square root, I'll end up in the second or the fourth quadrant. When the curve passes through the origin, again, it will connect the same 2 points on the imaginary axis to the same 2 points on the real axis. But it will do so passing through the first and third quadrants. Let's see. And let's see if we can see the same trajectories in 3 dimensions. And so this shows the same situation with the actual 3-dimensional vortex curves. And so with these 2 points at minus infinity and these 2 points at plus infinity. And this is the most interesting one. And so anyway, the point from this, we can see why in this situation, as long as this moduli space approximation is valid, reconnection is the almost inevitable consequence. Oh, here they go. So here, this blue is connecting to here at the top. Let's see. Okay. The buffering is not complete. So what you will see is that in the end, this connects to that and vice versa. And this thing changes colors in a way that has no meaning. Okay, let's see if it works. If I can, is there some way to minimize this? Okay, so that may start working later on, maybe not. Okay, and so then the point is that this moduli space approximation tells us why reconnection is the generic outcome of collisions. I'm using generic in a slightly vague sense here. In this setting. Here I also have an image of a curve that gives rise to non-reconnection, but these animations are not working super well. Okay, and so more generally, so here I assume that I was in this reduced moduli space where at every height and at every time the center of vorticity is 0. That was just for simplicity. So more generally, if I just define say d the discriminant of the polynomial in this way, then in the same way, a sufficient condition for reconnection is that the discriminant vanishes. So I have repeated roots, and the time and the y derivative of the discriminant are linearly independent. And so I claim this yields a large class of initial data that produce reconnection. It suggests that reconnection is the generic outcome of collisions. It shows that non-reconnection is a possible outcome. And let me say here, what I'm doing is I'm sort of assuming the theorem says that if I start with a wave map and I look at small enough epsilon, then the vortex filaments in the solution of the Abelian Higgs model will behave like the vortex filaments in the wave map. And so then I'm switching my attention to the wave map and saying, for which wave maps do we see a vortex dynamics picture who corresponds to connection? And I've lost the animation. Okay, and is this a universal mechanism for, so I argued before that reconnection is sort of universal, ubiquitous. Is this universal? No, not at all. I mean, it only applies to a handful of equations and only in this nearly parallel setting. But within that setting, it has rather broad explanatory power. So, okay, so in the remaining time, I'll talk briefly about the proof. I'll try not to finish too late, so we can get back to the closing ceremony if we wish. So, okay, so the proof uses ingredients from, there's a prehistory, Stuart Pavlev, also it was informed by work of myself with Zelpino and Musso. And so the strategy we'll use is a kind of if you like, a gluing or a Lyapunov-Schmidt reduction procedure. So we construct a approximation who solves the Abelian Higgs model to a very high order via essentially a rigorous asymptotic expansion. We then seek a correction U tilde, which will make this into an honest solution. The key point is always the choice of gauge. So we have to modify the equation for U tilde to fix the gauge and enhance coercivity. We prove linear estimates for the modified equation, and then we use these linear estimates to solve the equation via a fixed point argument. Here are some of the difficulties, and I should say that the analysis is in some ways quite different from the earlier work of Pavlov and Stewart. A number of new issues arise. And let me emphasize again that the main, I would say really the crucial points in the analysis are due to Masoud Geevechi. And okay, so here's the issue that arises throughout the analysis. This is essentially the gauge issue. And so let me write the equations in this fashion. I'll write I'll write the equations in the symbolic form S. Sorry, these are the 2D equations. I'll write the equations in the form S2D is equal to 0. And S2D is exactly the operator, the quantities of who I want to vanish if the equation is satisfied. Okay, and then if I have a configuration U, who I'll think of as being a solution, and a perturbation U tilde, I can define the linearized operator at U acting on U tilde in this way. This is the natural definition of a linearized operator. And the fact is that gauge invariance implies that this linearized operator has an infinite dimensional kernel, because the point is for any psi, if I look at U plus S, if I take a perturbation, G U star of psi, this is roughly equal to e to the I S psi phi and U plus S D psi. So it's this plus O of S squared. Okay, and so this agrees to linear order with a gauge transformation, from which one can easily see that that the linear operator acting on a perturbation of this form will give you 0. This is awkward for analysis. Okay, so I've restated back there. And so the point is that Stewart in his work introduced a perturbation of the operator. So he essentially said he notes that if we replace the linearized operator by this modified linearized operator, then this modified thing has much better analytic properties. We know exactly what the null space is. It's a two n-dimensional null space. We know exactly what the lifted tent, what it is, and we have coercivity on the orthogonal complement of that null space. And so essentially, I guess I think I don't want to go into more details in the interest of time, but so the point is, throughout the analysis, we have to work in order to replace the naive operator L by the improved linearized operator. So, for example, this means I'll just say this. We modify the equation in a certain way to improve the equation. I think maybe I'll omit these details, and thank you for your attention.
The comment about like 2D Geevechi model, we have this reconnection and Vortex.
Oh well, in 2D, the 2D counterpart of reconnection is this head-on collision with vortices scattering at right angles, and so yeah, so reconnection is really a phenomenon for, say, curves in R3, or you need say one-dimensional curves evolving in a higher space. You could look at curves in R4 also, curves in a dimension. So, but yeah, so the counterpart of reconnection in 2 dimensions is exactly the right angle scattering that we saw in that video. I'll see if I can get this going. Okay, so so this may start, it may not.
I'm not an expert in this field, but is it related to where the like Wilson line, like sending object in the gauge on the physical like that?
Sorry, what was your word?
Like Wilson lines.
Yeah, so these are right, and so yeah, I believe these could be called Boson lines. Yes. Okay, here it is. Good. Okay. So, okay, so I'm gonna. Yeah, the animation. So the I believe the slides will be put online, and I gave permission for them to be put online, and so you should be able to go to the slides and click on the link, and hopefully it will work better then. Yeah. You're welcome.
Where it comes, and in your result and the slide before, so
yeah.
One is T over epsilon, the other is epsilon T.
Okay, there was probably a misprint then, so they should both have been epsilon T. Okay, so so epsilon is here, and so what this says is that this is valid in the limit when epsilon is here, and so it's valid in the yeah. Well, so what this says is and so I have these curves in R3. And I have to look at a distance of order 1 over epsilon. To see order 1 change in the length of the curve. And then someone would have to wait for times of order 1 over epsilon to see order 1 evolution in the curves. And so this is the sense in which these are nearly parallel and slowly moving. This is the asymptotic regime in which this result is valid. Yeah, so the previous slides, yes. Well, in the yeah, sorry. This is a mistake. This should be epsilon T. I'm sorry. Yeah, so it should be F2. Thank you.
I'm wondering how's the right-hand vortex?
Good question. And so the, right, and so I draw these vortices with arrows, and the rule is that, so if I have a picture like this, with an arrow, I'd like to imagine that the vorticity is determined by a right-hand rule. So I put my thumb in the direction of the arrow, and and the flow is determined by a right-hand rule. And so if I have two filaments who collide, then essentially they have to if reconnection happens, it has to be in a way that preserves the arrows. So in this case, it would have to do this. If this were oriented in the opposite direction, then the only reconnection would be in that fashion. And so this is this would say that the right here this is the only consistent way of generating flow runs the rotation flow. Yes.
What exactly happens at the moment as the reconnection? For example, you could have, in my imagination, you could have a situation where the passing the reconnection time, the dynamics could be, so to say, ambiguous in the sense that either you can split this way or you can split this way.
Yes. What the theorem says is there is no. What the theorem says is the okay, if we imagine sitting in our laboratory and looking at the vortex filaments, we see them colliding and so on and so on. The theorem says the underlying reality is just a curve moving in the moduli space. And over here, nothing dramatic is happening. And
Well, in this really,
there's always this map, just the square root map from the moduli space to that yields that given a single curve here produces two curves there. And it's so this really describes the outcome of collisions. And it says that so the case in which you would not see reconnection is if I have a curve who comes down and touches here, and then so it comes down and touches, then goes back in the other direction, for example. And this would correspond to two curves who again have an oscillating collision and withdrawal. And so yeah, so that's the